Hello everyone, and welcome back. Last time we started to take a look at the mechanics of solids and fluids, and we are going to continue doing that today. So we're going to be staying in section 13, Mechanics of Solids and Fluids Continued. What I want to do is take a look at a couple properties of, in particular, fluids or liquids in this case, which have to do with the forces that the molecules or particles or atoms of the fluid itself, or the liquid, have for each other and for other things. Let's imagine we've got some fluid here, and let's imagine we're looking at the forces acting on one of these atoms or molecules of the liquid. So we're looking at a liquid here, actually. A fluid, remember, would expand to fill a container, but let's imagine we're looking at a liquid that is maintaining its volume. Each particle of this liquid is going to be attracted to other particles. There will be a force of attraction as long as they're not too close and they start pushing each other. So in the middle of the liquid, there will be forces acting on the particle, on each particle in every direction, and so we have basically a static situation. The particle is not going to be accelerated in any particular direction, or there's not going to be a net force in any particular direction. What if we look at the surface of the liquid? So imagine that we've got a liquid here and there's a surface here. There's lots of particles over on this side, but no particles over on this side. What are the forces going to look like acting on one of the particles at the surface? Well, the forces in this case will all be to one side. There won't be any forces acting on the particle in that direction. They will all be to the left, say, in this case. That's going to cause these particles on the surface to always try to minimize their shape in general, minimize the surface area. This creates what's called a surface tension. And it causes the shape of a surface to always try to minimize its surface area. That's why if you have a soap bubble or a soap film, it always minimizes the area between its surrounding border or boundary. So we have this surface tension that always tries to flatten out or flatten as much as possible, depending on the surface, the edge bounding it. Always tries to flatten itself out. So if you disturb this, like if you think about having a bowl of water and you hit the surface, you might get some ripples, but eventually those ripples will flatten out and the surface will again become flat. These forces for a particle with a similar kind of particle are called cohesive forces. Or this is called a cohesion. Cohesion means the attraction of something for other particles like itself. Cohesive forces. What if this were actually at the surface of a container? So maybe we had a container wall here, like the wall of a cup or something like that. So that over here we had atoms or molecules of a different kind of material. Well, it is possible that we could still have some forces attracting these particles to the particles of the bounding material. So these would be forces for a different kind of substance. These are called adhesive forces, or adhesion, the attraction of something for a different kind of material. So we have cohesion, which is attraction of something for itself, and adhesion, the attraction of something for a different kind of material. You might have heard of an adhesive, like adhesive tape. That's tape that you could put on something that's not tape, something different than tape, because that tape creates forces of attraction between itself and whatever you stick it on. So an adhesive uses adhesive forces. Okay, so we have this, the structure of the surface tension. When we have the surface of a material, it could be against the surface of a container, or just maybe in air, or perhaps even in a vacuum. Okay, very good. Now, let's take a look at what happens when we have something in a container and we look at the top surface. We can actually see the effects of the relative sizes of the cohesive forces to the adhesive forces in terms of what kind of surface it makes inside a container. Let me redraw this and take a look at that. Let's imagine we have two containers here, like maybe graduated cylinders or something like that. And we've got some liquids in each of these. I haven't drawn in the liquids though, not yet. But let's imagine for this one over here, the cohesive forces between the liquid particles and other liquid particles is greater than the adhesive forces between the liquid and the walls of the container. That is going to affect the material by making the surface of the material bow upwards like this, because the material itself is pulling on itself more than the walls are pulling on it. While in this case, if we had a material where the adhesive forces were larger than the cohesive forces, then the walls would be pulling on the material more than the material would be pulling on itself, and we would end up with the surface of the liquid looking like this, bowing down like that. These surfaces are what we call the meniscus. You might have heard about this if you'd taken chemistry or something like that. Meniscus. The meniscus. So the shape at the top can actually tell us something about the relative sizes of the cohesive versus adhesive forces. Now, if the adhesive forces are actually strong enough, if the sides of the container are pulling on the particles of the fluid strongly enough, they can actually draw the fluid up the sides of the container, and if the walls of the tube or the cylinder are small enough, they can actually draw it right up into the tube. And this is called capillary action. Or capillarity. And that's actually the way, or this actually helps trees get water from the roots up into the very highest parts of the tree. I mean, how does a tree get water that falls down on the ground, down where the roots are? How does it get its water up to the leaves that are on the outer and top part of the tree itself? It would be too high for it to like suck the water up, possibly if the tree were actually higher than 10.3 meters or something like that. Well, it actually has very, very small tubes, that capillary action, that actually capillaries, like we have capillaries for our blood, that actually help draw the water up into the highest parts of the tree. So the fact that we have these adhesive forces between the water molecules and the walls of the tubes in the tree actually help raise the water up to the highest parts of the tree. Okay, very, very good. Now let's take a look at what kind of a behavior the fluids itself will have as it flows along. So now we're going to start looking at fluid flow. Fluid that is actually flowing, that is moving. Let's imagine that we have a rather odd-shaped tube here through which the fluid is flowing. We've got a small section over here that then widens into a larger section over here. Let's see what kind of things we can say about this fluid flow. We're going to make first a couple of assumptions or a couple of approximations. First, we're going to assume that the fluid is incompressible. Incompressible. In other words, the fluid cannot be compressed. What that means is that whatever volume of fluid we have, that fluid will not change its volume. It's not going to expand, it's not going to contract. Another way of saying it is the density is constant. So we will assume that we have a constant density fluid. It's not going to expand, not going to contract. This is a reasonable approximation for many liquids. It's not a good approximation for gases, but for water, it's a good approximation as long as we don't change the temperature too much. So we'll assume constant density. Also, we're going to assume no losses, for the time being, no losses from friction. We're going to assume energy is conserved. No losses from friction basically means that there is no internal frictional forces. In other words, no viscosity. So we're not going to consider viscosity yet for our fluid. Okay, great. Well, let's see. Let's think about this. Let's imagine for this tube here, let's imagine we've got some opening over here with an area. We'll call this one A1. So A1, that's the cross-sectional area of this section of the tube. And then over here, we have some cross-sectional area. We'll call that A2. So remember, cross-sectional area, we could take this tube and look at it. What's the area of this opening? If it was a circle, pi r squared, something like that. And then this one, take this tube, look at it straight on. What's the area of this circle? Again, larger radius maybe if it's round, pi r squared, a larger area over here. Then let's imagine that the fluid over on this side is moving at some velocity. We'll call this V1. While over here, the fluid is flowing here, flowing out here. Then the fluid over here, we'll assume, has some velocity V2. Now let's imagine some time interval. We'll call it delta t. This fluid over here, in a time delta t, whatever is just entering the tube here in a time delta t will move a distance of v1 times delta t. So v1 delta t. So that's the volume of the fluid that will have moved that distance. So imagine what's going on here. In a time delta t, this fluid over here has moved over here. So all of this fluid, whatever is in here, has then moved over this distance, delta t. Well, if the fluid is incompressible, this volume, which has now entered this side of the tube, must then leave this side of the tube over here. If it's incompressible, whatever volume comes in must be the same as the volume that goes out. So, what's this volume? Well, let's think about it. If this is, imagine this is like a cylinder, the volume is area of the base times the height. So, delta V, we could say, is A1, V1, delta T. And then what's over here? Well, if this is like the area of our base, what height of this cylinder will have gone out? Let's call this some distance x2. What is that? Well, we don't have to do that. We don't have to write that down. What's the distance that this end will have moved? Well, if this is going a velocity v2 in a time delta t, the amount of this that leaves will be v2 times delta t. So what is this volume? Well, this volume will be area of the base, A2, times the height, V2 delta t. So this will be A2 times V2 delta t. Sometimes we might think of this quantity, delta V over, not velocity, delta capital V over delta t. This is called the flow rate, which is telling us the volume of the liquid per time that is flowing out of the tube. Delta V over delta T. What's the flow rate over here? Delta V over delta T is equal to A1 V1. So we have a flow rate over here of A1 V1, a flow rate over here of, I didn't write it out, divided by delta T, that is A2 V2. Because we're assuming an incompressible fluid, whatever volume flows in here must flow out over here. Whatever time interval we have here is the same as the time interval over here. So we must have our flow rates equal to each other. In other words, A1 V1 must equal A2 V2. There we go. This is called the continuity equation. And it comes along because, or it comes out because we are assuming an incompressible fluid. In other words, whatever volume goes in has to be the same as the volume that comes out. The volume can't be compressed or changed. Very, very good. Okay, what can we make from this? Where can we go from here?